Dr. Sharara is in the Biological and Agricultural Engineering Department, has a research and extension program that's really, really impressive, does a lot of work with animal manure, mortalities, and other byproducts, looking at the technological and economic assessment, as well as life cycle assessment to really develop sustainable practices. We're pleased to have you with us today, Mahmoud. Come on up.
Thank you, Dr. C. Thank you, everybody, for being here. I'm learning quite a bit. As you might notice, the presentation is a little bit of a different side of the production, but it's, I argue it's as important, and the sustainability of the system is as good as the weakest or the least sustainable part of the system. So my talk to you all today will be about nutrient management, but from the swine manure side of things. And really, my goal today is to kind of share with you a little bit of some of the work we're doing, a couple of studies that we have wrapped up, and some of the interesting data analysis of where manure management is. And befittingly to what Dr. Flowers and Dr. Knauer mentioned earlier, climate is a big piece, not just from an animal welfare and stress, but also as it relates to manure management or nutrient management on the farm. We looked a little bit after that into the manure management as it happens today, and then I transitioned into the needs and opportunities based on what we've seen and what's next. And I look forward to hearing your feedback on that work. And looking into what I call is the new normal. This is actually the term that NOAA uses to describe normal climate patterns. It's basically an average of 30 years. So the previous normals that were used were 1981 to 2010. After 2020, that has shifted. So we dropped the 80s and it's 91 to 2020. And what you're seeing here on the left side is the change in temperature. So this is the orange, the darker, the orange is the warmer we're expected or we have seen with that shift. And with the exception of the upper part of the plains, it's primarily warmer. And on the right-hand side, you get to see where North Carolina is at. So we are seeing temperature. And again, this might seem like a small change, but this is an annual average. We all know that we don't really see the hottest parts when we look at the averages. So that's sort of an aggregate, but gives you an idea of the trends and the patterns we're seeing with weather, and a little bit here too in precipitation. So precipitation really, from a humidity, we put those together to get an idea of the heat index when it comes to the production. But from our side of the production system, precipitation means water falling in lagoons. That means an added volume. And the conversation I always have with a lot of the swine experts or manure management, even from different parts of the country, is our pigs produce more manure, even though it's the same animal units or daily gain. It's just the dilution creates a larger burden for management. And when looking at this particular trend, that tells you that clearer. This is kind of a summary of the Climate Office data that we have here for the weather station in Clinton, in North Carolina, and seeing kind of trends on an annual aggregate rainfall that we've been seeing. If you look closer, you'll see that the trend is about 1.7 inches of rainfall added every year. Granted, this year has been dry, so we'll wait to see how it checks out, but just September and October have a way of making up for the rainfall during the year. So really, this kind of sets us up from a weather, temperature, and rainfall. And really what it means to swine production, specifically to manure management on individual farms, that means that we have more volumes that needs to be managed. We have less time to manage it, considering the amount of rainfall and the conditions of fields, with saturated fields inaccessible or should not be used for application. And the third, and we've been seeing it more noticeably, and in talking to my colleagues around the country, this is something certainly we observe, is the attention that the non-production practitioners give into swine production, in particular here in North Carolina, and how manure is managed, where it is applied, or when, how frequent, the equipment. So all of that can create a lot of pressures on the management. And where you can see the plot on the bottom part of the slide shows you the averages that we get to see every month in terms of rainfall over the last 20 years and the extremes that we've seen Most of the extremes, if you look closer, have been observed during the last 5 to 6 years. And a lot of them happen and do coincide a lot with our cropping cycle or cropping months, so the typical March to October. So really, we see that water is a big part of managing manure, and a lot of it is water that has not been excreted by the animal, which is a really big challenge. But if we started to look at the nutrients that we actually bring into the farm for the production, for the explicit purpose of raising animals, and what you're seeing on the slide behind me is the nitrogen in particular, and I'm focusing on it because it presents the bigger opportunities, and especially looking at the markets and the prices for inputs to production. That's a clear opportunity of what is being wasted here. So from 100% of nitrogen entering the farm, less than 40%, more realistically 35% of that is captured in animal weight gain and leaves the farm, with closer to 7 to 10% of emissions in the houses or in the barns themselves. And the rest of that nitrogen leaves and enters our lagoon, where the majority of it leaves the lagoon as emissions, both as ammonia and potentially nitrogen. And again, potentially as nitrogen because, believe it or not, our system has been in practice for a very long period, but we do not have robust data on tracking the nitrogen on a large enough farms in terms of where the fate of the nitrogen that we do not use beneficially. But what we use effectively, both for animal weight gain and for cropping, represents much less than 50% of that nitrogen. So in the best case scenarios, some of it would be lost as nitrogen gas with minimum impact on environment. Worst case scenario, a large percentage of that we're not utilizing is leaving as ammonia. And ammonia has been a recent attack point or potential limitation that the industry is having to contend with. Not just the swine industry, but the dairy industry in general, any industry that is looking into capturing the energy potential of manures, and it's being put into as a condition to a lot of the upgrade technologies that we're looking to put on our farms. So what we're looking here at is on this slide is what do we do with that 2 to 3% of the nitrogen that enters the farm and we utilize as cropping. And the point that I want to draw to your attention, how much of that nitrogen goes back to support the swine production, specifically in terms of corn and soybean. And granted, we are not the largest producers of both or either, but we see that soybean and corn represent much less than closer to 25% of the actual acreage that receive swine manure nutrients or nitrogen. So that again is another opportunity of trying to make sure that we have the nutrients in the farm to support more of the feed going into this production. Again, this is a summary of records for, as you can see in the caption there, 19 swine operations. And we track their irrigation records for about 6 years to get a better and quantitative idea of the nutrients and how they are being utilized. And the other part, which I've been talking about for a lot of you that have talked to me, I've always, lagoons and lagoon sludges always came up. So, and I appreciate the interest, and I see a lot of the work here, interest on the topic, but really primarily because what you're seeing here is from a large data set from a lot of operations, and we're seeing here between 27 operations that we've been tracking their data over 6 calendar years, we're seeing closer to 38% or more than a third of those by operation requirements have to remove sludge in order to be compliant. And for many of us, that means that this is a significant amount of nutrients that have to be removed or excavated from these lagoons for utilization. And whenever that happens, we really have to contend with how it is managed on our farms today. And what I'm showing you here, this is an average of the data records that agronomic labs here in CDA receives. That's an average of closer to 5,000 individual samples that we've aggregated by total solids to really define the management from either it's pumped and hauled as a slurry or as a solid being handled. In both cases, the point that I want to draw your attention to is the nitrogen to phosphorus ratio. And those are numbers that are very clear to a lot of our agronomic expertise or folks with cropping expertise. We never really need nitrogen to phosphorus ratios that low. Primarily, we need nitrogen to phosphorus ratio 3 to 4, but we're seeing it in the opposite direction, higher phosphorus than nitrogen. So really that creates a challenge to where we are limited on the acres we can access to use it because of phosphorus, or we risk adding more phosphorus that a lot of our crops need or can tolerate. The amount of waters that we're contending with for management is another limitation. So really this kind of rounds it up. And again, it's not really a bad news bearer message, but it's more about the opportunities or what are the real needs. And I look forward to hear your feedbacks on this, but the primary priority is resiliency for rainfall, essentially a flexibility to operate without having to manage around a rainfall calendar. Also, there is a significant need for utilization options for sludge that are economical, more affordable to our growers, as well as looking for realizing the full value of the nutrients that we know exist in the manure, whether we're actually reducing these losses or accessing markets where they can be utilized beneficially. We're also, to do that, we need to access export of these nutrients and ensure that we are reducing these emissions. So to do that, I'll talk to you about a couple of projects and the data we've managed to present in a couple of venues and a project kind of a highlight. So really, the first two projects I'll talk to you all about relates to these lagoon sludges and to trying to make them in a more agronomically acceptable form to where they can be applied on a wider range of cropping or soils, as well as creating a more compact form material that could potentially be used for land applications, but also, and some of the poster I was glad to see Dr. Van Hooten's team and the poster about the utility of sludge dried materials. So really, from a composting standpoint, we really sought to answer a few questions. Can we utilize composting, which is a famously low technology option in terms of inputs and requirements on farms to compost or create a stable product from the sludges that we recover from our lagoons? And can we rely on a lot of the locally available materials that otherwise are undervalued? It can potentially be a limitation. And how much of that sludge can practically be utilized in this technology? So what you're seeing on the bottom part of the slide, these are pictures of some of these feed ingredients that we use to formulate these recipes. So these are Bermuda hay, and when our cattle growers are really not in demand for it, or when it's high in nitrate content, it can be potentially a burden for some of our growers. We looked into using the lagoon effluent itself as a water or a moisture source in the recipe to reduce water use and at the same time create an input, as well as looking into poultry litter, tree trimmings, and obviously the sludge itself. We formulated two different recipes with the 10% and 20% inclusion rate of that sludge into the compost recipe, along with these locally available ingredients that you see behind me. And we set out the temperature, weight change over the compost period, as well as the moisture change, looked into the nutrient fate, both retained nutrients, but also water extractable. Primarily, and we also looked into greenhouse gas emissions. I'm not going to be able to present it today for time, but we presented that in a couple of venues, and I'm happy to share with you our publication on the topic. And what you're seeing on the other side of the screen here is these modules we used to collect a lot of this data on our university farm. And what we've seen and kind of broad results is that we were successful and the material was very conducive to the composting process. And the ultimate test we use is the temperature that we're able to achieve. We're able to achieve more than 12 days where the compost pile was over 130 degrees Fahrenheit. That 130 degrees Fahrenheit is a threshold that our Department of Ag designates to create a product that has been acceptable, essentially went through a bacterial kill. And what you're seeing on those two lines are core of these compost piles averages over that period, and multiple heat cycles that once we mix our compost piles, we start again, and comparing that to the diurnal daily cycles in the yellow at the bottom of the figure. And what you're seeing on the upper right corner here, this is an infrared image showing you the temperature when we actually open up these modules and showing where these sensors are. We also track the weight loss for these piles, and we're able to see closer to 40% weight loss and a significant moisture loss as well, where we started with 65% moisture and made it closer to 40% moisture or less. And when we sent it out to make sure that we have the agronomic quality of this material, it's been classified as a stable mature compost. The seedling emergence was greater than 92%, which is typically one of the thresholds for deeming it acceptable. And looking at the plant vigor, seedling heights, a lot of these, it passed it with flying colors and created a much more acceptable nutrient ratio compared to what we started with. And in the process, we didn't have to really rely on high cost inputs to really create something valuable for agronomic purposes. So really from an application standpoint, this is again, a viable option. That became a tool that we can add to the toolbox, and not just for sludge management, but also for that liquid or effluent that these lagoons have to contend with managing every year. And we're also looking into value-added products, and this is an example beyond just compost that's sold bulk. It could be upgraded, prilled, or sold for niche markets where a higher value can be realized. So really beyond this, we also sought out a much more aggressive option for lagoon sludge, which is drying. Essentially trying to dehydrate it completely to create something that is more biologically stable, that could be exported, and could be formulated for more professional product lines for fertilizers by potentially fertilizer companies. And we sought to look into the performance of greenhouse structures as an option for drying these sludges and what's the cost involved with it, and comparing that cost to what are the technologies that are currently used with industrial sludge management, primarily for wastewater treatments. And with this, in a collaboration with our integrators, and we're looked into two greenhouses here built in Eastern North Carolina, and we've collected data. And what you're seeing here is the cycle of how sludge has been dried. Essentially, again, the emphasis here was on the low-tech aspect, essentially to make sure that we are introducing a technology that can realistically be operated day in and day out without added burden to our operators. So what you're seeing is the loading of this material closer to 80 to 82% moisture, loaded into the greenhouses as similar to putty texture, and using just a regular tiller that has been modified to affect the drying and expose a lot of the surfaces, and relying on mechanical drying in this example with 24-hour continuous ventilation and observing the temperature. Again, the data that I'm showing you today for a period of drying that occurred from January to the end of February. So really the coldest 2 months of the year. And if you can really look into the lower right corner of the slide behind me, tells you that we were achieving over 90 degrees simply because of that greenhouse effect that we're able to leverage. And if you see here on the horizontal axis, we're looking really in weeks. So we're right by the 6-week mark. We were able to reduce the moisture from 80% to 25%. I'm using here dry basis units, which we use it for reporting, but really we basically created a material that is stable, that could be transported safely as a material for lane application. It could be formulated or prilled as well. And we converted this into, there is a typo here, but we are tracking 2 greenhouses, so house 1 and 2. And really we tried to benchmark them in terms of pounds of water that we're able to remove from a square foot of footprint per day in order to try to upscale this and create design coefficients for different farms with different rates of sludge that needs to be removed. And we're observing during that coldest stretch of the year between 0.5 and 0.6 pounds of water per square foot per day. So that really gives us a better idea of the throughput that we can realize from different footprints, 5,000 to 10,000 square foot structures. And what I'm showing you here, this is an economic assessment that we've done with consulting with the several technology providers, 4 technologies, and they're named options 1 to 4 here. And this is really looking at the cost of producing a ton of dry sludge-based product in dollars. And you can see here the different colors represent whether it's the capital cost of the equipment or it's the amount of electricity consumption, heat, or labor. And what you can, I want you to take a look at here is the primary that the cheapest cost you can dry material like this is $100 roughly, and it can go up to $170 per ton. With a significant part of it is the capital cost and the heat requirement for industrial drying. When we shift into the technology we looked at and we stacked the numbers to achieve the same moisture content, we realized that we're able to meet that with only $40 per ton. And that's without optimizing the technology to actually reduce the electricity consumption for ventilation as well. So really, we're seeing that this is a low-tech technology. You're seeing on the upper right corner here a picture of these greenhouse drying structures. We're also seeing opportunities for upgrading it to pelletize and to combust in order to access these minerals in the ash. Also, although based on a lot of the findings, we're able to realize digestibility of that phosphorus, even only in the dried form. So that becomes a much more valuable utilization approach for these nutrients compared to land application. So really, a technology like drying allows a lot of our growers to access options to compare end uses for this sludge beyond just land applying in the closest available acre, at times at a cost to the grower. Now that reverses the paradigm to where high-value markets for phosphorus can be accessed or long-distance transportation. So you're seeing here on the lower pictures, some of this material has been drilled, and we've looked into the data. I've actually traveled and looked into it with some of our integrator experts. So that's really interesting to see whether there are existing markets and some deployment of this material out there. So kind of to sum up and give an opportunity for some input questions is climate is a big driver of how not just swine production proceeds, but also manure nutrients are managed. We see a tremendous opportunity to improve the utilization of these nutrients, both to reduce losses, but also to realize the economic value of these nutrients. Logistics has been a big barrier, and the form of these nutrients and their ratios. A couple of these technologies are both low-tech and promising in terms of the value that we can realize from these manures. And finally, I want to leave you with this thought, which is to achieve the independence from this rainfall, it's the lagoon covers. And we understand that this is an important proposition, but it has implications on nitrogen or how we are managing nitrogen on our land base. This is some of the work that we are working on right now, and stay tuned. I hope to be here next year and talk to you about some of what we're finding from a cost perspective as well. And with that, I want to thank a lot of our funders and a lot of the students that helped me with this work. And thank you all for being a great audience. Thank you all. And I'm told there is a time for a question, so no pressure.
That clear.
Okay.
Your trial, what method did you use to capture the sludge from the lagoon?
That's an excellent question. The question is, in the trials, what was the method used to capture the sludge from the lagoons? Part of our research projects, we actually looked into different dredging pumping apparatus, and didn't get a chance to report here. But in the composting study, we started already with material that has been bagged, essentially polymer treated and put in water in bags. So we started with a 20% solid sludge. However, in some of the other studies that we've been using pumping apparatus to collect the sludge directly from the lagoon, we're able to hit between 11 and 15% solids.
Some nutrient use of the phosphorus. Is there a difference between the drying sludge in the greenhouse and the composting sludge with components also involved?
That's a really good question. The question is there, from a phosphorus perspective, is there a difference between the drying and the composting of sludge? And a key point I didn't get to report here, but when we tracked how much of the phosphorus we have is water extractable, which means that from a rainfall can be potentially lost from our material. We found that composting as a process and with a lot of the humic substances that are generated actually binds a lot of that. So we conserve a lot of the phosphorus from losses. So it becomes more available in the soil compared to the way it's removed in sludge format. We do not have agronomic data yet on the dried sludge. My colleague, Dr. Kaleza in Crop and Soil is running both incubation and greenhouse trials, and you should be having some results soon to share with you all as well.
Thank you.
Thank you all.